All right, so there's going to be a walkthrough for the fifth worksheet, practice worksheet for Organic Chemistry 1 in autumn 2025. So this is going to be covering mostly stereoisomerism, or well, everything that related to stereoisomerism. So let's get started with chiral center. So what exactly is a chiral center? A chiral center, or a stereogenic center, is any carbon or any other atom. It could be a nitrogen, but for the purposes of this class, we'll just focus on carbon. Any carbon that has four different things around it. So if it has four things around it, would mean that this carbon is sp3. It cannot be sp2 or sp, it can only have sp3, right? So here in paclitaxel below, let's just start looking for these. I usually indicate a stereogenic center with an asterisk, so I'll just do that right now. I see this one, we have an H right here, so that would be four different groups. This carbon, this carbon, this carbon. This carbon isn't a stereogenic center because it is an alkene, it's sp2. But I also see this one right here. This one right here because it has a hydrogen. This carbon alkene, not an alkene, a ketone, alcohol, and another carbon that's connected to these groups. This one right here. This one because it's connected to this oxygen, and this other one, and this other carbon, and a hydrogen. This one right here. And let's see, also this one. Anywhere else? No. So in total, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 chiral centers. Cool. All right. The second question is pretty heavy, but before we talk about enantiomers, diastereomers, all that, I want to talk about RNS. Okay, I know a lot of people who come to the TLC or anybody who I'm tutoring, they get stuck on stereoisomers because maybe they're not skilled enough to rotate or manipulate the molecules in any way to determine the stereoisomerism, right? So if you're not able to do that, please use RNS configurations. I swear, doing the actual RNS configuration only takes like about a few seconds, okay? But with enough practice, it really should not be that hard, right? So what is RNS exactly for? It's very, very, very helpful to determine the relationship between two molecules. That is, okay, if I'm looking at this one, are they enantiomers, diastereomers, etc., right? So I can easily do that. But in order to actually assign them, I need to know priority rules. And really, the biggest one, the first one you should know is that the highest priority goes to the one with the highest atomic number. Okay. So if, for example, I had this bromine, chlorine, maybe an ethyl here and a hydrogen here, bromine gets 1, chlorine gets 2, hydrogen gets 4, what am I doing? 4, and ethyl gets 3, what am I doing? Okay. If for some reason we have multiple bonds, I'm afraid I'm going to have to actually explain it in a different way because I suck with words. So let's say I have this methyl in the front, hydrogen in the back, and what if I have, actually no, I'm going to make this an ethyl. So we have two carbons in both chains, right? So let's just assign number 1 and 4. 4 will usually just be a hydrogen or a methyl, so, but now we have these two. They're both carbons, but, there's not really any way for me to differentiate outside of that. But what I can do is do a little bookkeeping trick. I'm going to say that this carbon right here is bonded to 2 carbons. Why? Because I see 2 bonds. This carbon has 2 bonds connected to a carbon. So I'm going to convert that and say carbon is bonded to two other carbons. If I had, for example, this ketone, or well, this carbonyl, right? Two bonds bonded to oxygen. Now I'm going to say two bonds connected to two oxygens, or well, one bond connected to two oxygens, or whatever, right? If I had a nitrile, which is a C triple N, then I'm going to say this carbon is bonded to three nitrogens. I hope you're getting the gist here, okay? So, if this is the case, they're both carbons, right? But now I can actually say, okay, I'm going to call this R, BR, whatever. This carbon is bonded to two other carbons, while this carbon is just bonded to one carbon. Who wins? This one. This alkene versus an alkane. Alkanes are pretty boring. I guess you can think of it like that. They have a lower priority. So this one gets 2. This one gets 3. So those are some rules as to when the hydrogen or the lowest priority is in the back. Let's talk about if the hydrogen is in the front. Never gets too simple, right? So if lowest priority is in the back, in the front, let's say, for example, I have a hydrogen there, chlorine here, and maybe an ethyl right there. Okay, so if the lowest priority right now here it's a hydrogen, I can assign like normally, but then I have to do something else. Excuse me, hold on. Okay, yeah. So if this hydrogen is front, I can just assign like so to 3. Let's trace an arc. 1 to 2, 2 to 3, 3 to 1. This is actually S for left, but no, this hydrogen is in front. No, it's actually R because a hydrogen is in front. So again, just to sum it up, if the lowest priority is in the front, I can assign like so, but then my configuration has to be swapped at the end, right? Also, I didn't do it right here anyways, but like if I can assign the priority, or well, the configuration 1, 2 to 3. This is S for left. Ew. What am I doing? Hold on. Okay. 1, 2 to 3. This is R for right. Stupid. Okay. The last thing I'm going to cover for R and S is if the lowest priority is what? In the plane. Thank you, God. Okay. Instead of hydrogen, I'm going to do something spicy. Maybe I have an ethyl here, chlorine here. Maybe I have that there. So I know that my highest priority, actually, hold up. Wait. Hold up. Okay, so if the lowest priority is in the plane, here it's going to be this ethyl. We know that the alkenes take higher priority than alkanes. So since the lowest priority is in the plane, I have to actually swap so that the lowest priority is in the back. So I'm going to switch these two. Okay. Bromine, okay, ethyl. Okay, and then I'm going to assign like so. 1, 2, 3. This is S, but it's not S because I had to swap things around. It's actually R, okay? Do not get fooled. If I catch you on a quiz or an exam doing that, you did not swap it, I'm going to hunt you down, actually, okay? So this is just a little overview for RNS. Please use it. Please, please, please use it. If you are unable to like rotate or manipulate the molecule in any way to determine the stereoisomerism, please use RNS. I beg. I beg. Okay. So that's RNS for you. Now, let's talk about enantiomers, diastereomers, and whatnot. We know that constitutional isomers is just the same formula, but different rearrangement of atoms, right? But enantiomers and diastereomers, they're stereoisomers. They have the same formula, but they're rearranged differently in space. Okay? So, what is the difference between enantiomers and diastereomers? Enantiomers are mirror images. So if you look at your hands, this is like a good example of an enantiomer. They are mirror images. No matter how much you flip it or rotate it, whatever, your hands won't exactly superimpose, meaning like they won't really lay flat against each other so that the it's like saying, okay, a left hand is only a left hand. It will always be a left hand no matter how much you flip it, right? So that it cannot be a right hand. But a right hand is always a right hand no matter how much you rotate it, flip it, or whatever. A right hand cannot be a left hand cannot be a right hand. So this property is intrinsic. So no matter how much you manipulate it, it's always going to be that. So for an example, if I take this molecule here, hold on. If I take this molecule and reflected it, then I would get something like this. No matter how much I rotate this this molecule around or flip it or whatever, they're not going to be the same. If I offer the top view, maybe like so bromine, and then chlorine here, then the hydrogen's right there. No matter how much I rotate this one, maybe I can help try to convince you. I can like say, okay, this hydrogen, this methyl, this chlorine, right? Can't exactly swap this around or well rotate the bonds around here. So if I rotate it, sure, I could probably have the chlorines try to match up. Chlorine's right here, but then the, what's it called? Methyl will end up here, and the hydrogen will be here, right? And that does not match up with this. These do not match up. So these two are enantiomers. They are mirror images. Okay. Mirror images. Enantiomers. Of course, these are just simple molecules. They can get even more complex as you go on. Let's talk about diastereomers. Diastereomers are not mirror images. Diastereomers, I think, are actually easier to identify than enantiomers because for diastereomers, you need more than 2 chiral centers. And as always, you can always just resort to RNS configuration. So for example, if I had this kind of molecule here, and maybe I had this, BR. I can actually see that the stereochemistry of this carbon stayed the same while this one was flipped. So these are diastereomers. Yeah, diastereomers are much easier to actually identify than enantiomers, in my opinion. And I guess another one that we'll talk about are mesocompounds. Mesocompounds are achiral. They can have chiral centers, but those okay, yeah. So mesocompounds can indeed have chiral centers, but they also exhibit an internal plane of symmetry. So, for example, if I had maybe this, BR and BR, this has an internal plane of symmetry, meaning that this is achiral, actually. It may have chiral centers, but because it has an internal plane of symmetry, it's a mesocompound. So if I had another structure that is that maybe has like a constitutional isomer or whatever, hold on. So if I had this, because these are they have an internal plane of symmetry, these are just mesocompounds, and they're identical. Okay, easy. I promise, it's easy, okay? So let's just look at these questions here. I'm only gonna do a few of them for you, with you. So, number one here, I can see that this hydrogen is in the plane, so I have to swap with whatever is out and behind the plane, right? So I'm gonna swap these two. And so if this is a bromine, and this is a hydrogen, I can assign like so. Bromine to methoxy to methyl, 1, 2 to 3. This is going to be R, but it's not R because the hydrogen was in the plane, so it was actually S. Hydrogen's in front of me, so I can assign like so. Bromine, methoxy to methyl. This is R, but since the hydrogen is what's called in front of me, it's actually S. They have the same oh my gosh, I cannot speak. Since they have the same configuration and they're made of the same molecules, all that, these two are identical. Okay. Very cool. This one, the next one right here, we can kind of see that the methoxys here are kind of mirrored, and the NH2 are also kind of mirrored. So if we drew a mirror here, we would get exactly that. So these are enantiomers. I can also prove it with the R and S configurations. If you are not able to quickly identify and determine and say that, okay, these are enantiomers, use R and S. Do not feel bad. It is not a crutch. I swear, people use R and S all the time. Please use them, okay? Never feel bad for using a very helpful tool. So, if I have NH2 here, then I know that the H is in the front. So 1, 2 to 3. Since the H is in front, it's actually the S. Right here is 1, 2 to 3. S, but it's actually R, since hydrogen's in the front. Methoxy, 1, 2 to 3. It's S. Yep. Methoxy, 1, 2 to 3. It's R. Okay. Both of these are flipped. Not only one of them. If one of them was flipped, then it would be a diastereomer. But since both of these configurations flipped, then they are enantiomers. Okay? All right. Let's look at this one. I actually stole this from Alex. So if you actually saw this or thought this was familiar, then yes, this is familiar because I stole it from Alex. Actually, did I steal it from Alex? I don't think so. Whatever. I think I stole the other, these two from Alex, but not this. Actually, no, I didn't steal any of these from Alex. Sorry. Anyway, if we drew a mirror, they kind of look like enantiomers, right? But notice that the double bond, or well, notice that the what's it called? This wedge turned into a dash, right? So if I flip this, if I flip that, then I would get this. This double bond would be there, and then that, and then that, right? So these are technically identical. Okay. Again, I'm not going to do all of these, but I will do some. This one, I like this one. This one, they're obviously not identical because there is a wedge here and this one's a dash. But let's assign the R and S. Nitrogen goes 1, 2, 3. 1, 2 to 3. This is S. 1, 2 to 3. This is S. But since the hydrogen is in front, it's actually R. And let me tell you a funny thing. These two are forms of methamphetamine. Methamphetamine exists in two forms, the S and R. But the R form is actually safe for medical use, I believe. Yeah, so the R form of methamphetamine is safe. In fact, it is an active ingredient for a Vicks vapor inhalant. Like if you have like congestion in your nose, then you can use like vapor. So you're basically using meth. So yeah, this one I think is the illegal version, sadly. So yeah, I thought that was cool. Anyways, let's look at number 3. We're back to Newman projections. How fun. For Newman projections, I actually like to approach this. So like, if I were given, let's compare A and B. Let's look at the front carbons. The front carbons look exactly the same, but the back carbons don't. Can we rotate the back carbons so that the back look the same? So let's rotate B, back carbon. If we rotate the OH to be the same position as this, then yeah, we get the same. In fact, like rotate this to that, this to that, this to that. So these are identical. Okay. If we're comparing B to C, the front carbons kind of look like they're mirrored, as well as the back carbons, right? So CHO, CHO, the methanol, methanol, okay? So these two are enantiomers because you can see the mirror, Teomers, okay? And C to D, we can see that the front carbon is the same, but can we align or rotate the back carbon so that the OH is aligned, right? So if we rotate this, the OH is going to be bought, the CH2OH will be on the left, and the H will be on the right. So if the front carbon's the same and the back carbons are different, then these have to be diastereomers. If you even want, if you're not able to look at them through a Newman projection, you can also look at converting each of these into skeletal structures. That I will not be doing in this video because that takes a while. Let's look at A and D. Come on. Oh my gosh. Okay. A and D. So, the front carbons look mirrored, the back carbons look the same. So let's see. Actually, yeah. Oh my gosh. Yeah, okay. So if the back carbons are the same, but the front carbons are not, then they have to be diastereomers, right? Because that would imply that the stereo, or like the RNS configuration would be different. Diastereomers. So basically, if I can rotate the front or the back to look like one of them, or like if I compare these two, oh my god. If I compare these two and I see that the front carbons are the same but the back carbons are not, maybe I can rotate it so that they do look the same. And that's what happens here in A and B. But for B and C, I can see that there's a mirror here. OH to OH, CH, OH to OH, HH. They're enantiomers, right? For C and D, maybe it's not that simple. I can't you really use a mirror, but I can see that the front carbons are the same, and the back carbons, no matter how much I rotate it, they're not. They can't really be aligned so that C and D look the same. So they're diastereomers, and same with A and D. So hopefully that makes sense. Number 4 is a bit trickier. So let's look at it a bit more. Can we rotate, or well, let's just know what we can see. The the front carbons on both of them look mirrored. But the back carbons look different, right? So, if that's the case, can we rotate the methyl and the methyl here to kind of align with each other, like in on the left one? So if I rotate it, then I would have, CH3HO, the front carbon stays the same, but the CH3 in the back, the OH and the hydrogen are different. So the methyls are aligned with each other. Oh my gosh, what am I doing? Hold on. And the alcohols, blah, blah, blah. So we were talking about meso compounds before. We talked about, okay, they're achiral and they have an internal plane of symmetry, right? Could that be a possibility here? Well, we can see that there is. OH, OH, CH3, CH, hydrogen, hydrogen, right? So there is indeed a plane of symmetry. And if we rotate this one, we can also see that as well, right? If we also slice this in half, we cannot see that actually, never mind. Never mind. So because there's a plane of symmetry, sorry, this was a trick question. These are meso compounds. And so since they're meso compounds, they are identical. Sorry. Hopefully that didn't upset you. Anyway. Okay. I will not do any of these except for this one. I'll do this one because this one's a bit tricky, right? Okay, so let's just look at if there's any stereogenic centers. Well, this one looks like it has 4 different things around it, right? So let's try it. Let's try to assign it. Let's see, 1, 2. Well, this carbon leads to this, and this, and this, and 1, 2, 3, 4. This carbon leads to this, another one, and then another. So the fact that they both paths lead to the same thing in the same number of moves, I'd say, these two are not actually different. They're the same. So this carbon is not a stereogenic center. Right? Same with this one. This is not a chiral center. Not chiral because of the same reason. Both paths lead to these two substituents in the same, number of moves. 1, 2, 3 alcohol, 1, 2, 3 alcohol. So this is not chiral. We cannot assign R and S. Okay. Hopefully I didn't upset you guys with that one. So let's talk about optical activity. So essentially the thing is okay, if I have a sample of a mixture and I wanted to see what enantiomer it is, right? Maybe it's R, maybe it's S. if I shined a light through the sample in a polarimeter, then the enantiomers, R or S, will bend the light either left or right, right? So um, since we're looking for the inactive one, we want one so that, like, okay, maybe there's no chirality because if we see a bend in light in a polarimeter, there's going to be chirality. We're expecting that there's going to be chirality. So optically inactive is also just another word for for saying, okay, is this meso or achiral? Let's see. There's no plane of symmetry here, so this is chiral, meaning optically active. This is not symmetrical at all. Let's see. No symmetry here, so it's not a meso compound. This one is a meso compound here, so this is optically inactive. Cool. Okay, so let's talk about enantiomeric excess. And I swear, I'm not good at math, but the math is okay. The math here is okay. Do not worry. Do not worry, okay? So I'm only going to do the set for 27. I'm not going to do the last question either because my throat hurts. So given the specific rotation, which is these alpha, given the specific rotation of pure R-ibuprofen is plus 54, calculate the enantiomeric excess of a solution with the following specific rotation values. And this is the mixture. And for calculating EE, I know that I can use either two formulas. EE is equal to the percent of one enantiomer minus the percent of the other. Or I can use the EE is equal to the specific rotation of the mixture divided by the specific rotation of the pure times 100%. Okay? So let's do exactly that. I'm not given the percentages for this first question, but I am given the rotation. So I'm going to use the bottom formula. EE is equal to alpha mix alpha pure times 100%. So 27 divided by 54 times 100%, and I believe that would be 50%. Cool. For each enantiomeric excess, calculate the percent of each enantiomer. One quick thing. So let's say I have 100%. This is going to be my total. Minus 50%. This is going to be my enantiomeric excess. I know that my excess is going to be the R version because, what was the reasoning? Oh my gosh. I know that my excess is going to be R because it's causing the plus 54, right? If it's going to be more S, then we would have like a more negative number in this case, right? So I know that my excess is going to be in the R because I'm given this, right? So if I took away the excess from the total, then I would get 50%. Yeah, leftover, 50% leftover. This 50% exists as a racemic mixture. Racemic mixture just means that it's equal parts of both enantiomers. So in other words, this 50% is made up of 25% S and 25% R. So in total, I know that I have a 25% S and I have 50% of excess plus my 25% R from the racemic. That gives me a total of 75% R. This gives me 100% total. So like if that kind of makes sense, if that didn't make sense, excuse me. Hold on. Oops. I need water. Okay. So, if this kind of didn't really make sense, I want you to imagine a jar, right? Maybe I have a jar filled with jelly beans. And I want to know, okay, maybe I have red and blue jelly beans, okay? I have a mixture of red and blue jelly beans. I know that I may have like an excess of like blue jelly beans. So what if I took the excess out? Now I get a racemic mixture or an equal mixture of red and blue jelly beans. So I have the excess percent of blue jelly beans plus the blue from this racemic mixture, as well as just the racemic mixture. I mean, what the hell? And just the percent of red jelly beans. Hopefully that makes sense. It made sense in my head, but whatever. Anyway, for C, I know that for our ibuprofen, it's plus 54, and I know that if the other enantiomer bends light the other way, then the rotation should be alpha equals negative 54. Okay? If a solution contains 60% R and 40% S, what is the enantiomeric excess of the solution? I'm not given the same thing like this stuff, but I am given the percentages. So I can do 60% R minus 40% S. Then I would have a 20% excess of R. Okay, and since I have a 20% excess of R, I want to know the specific rotation of this solution described. So I know that EE is equal to the specific rotation of the mixture divided by the specific rotation of pure times 100%. Well, if the specific, the enantiomeric excess is 20, and I know the pure for R is 54, I don't know what the specific rotation for the mixture. I can do a little bit of math, okay? I can rearrange this so that the alpha mix is equal to 54 times what? 20 over 100. And so this should equal like, what, maybe like, this should equal like 10.8 or something. Yeah, and it would make sense because the plus would still mean I have the R, right? Because pure is plus 54. If I had like a 20% of excess, then like I would have 10.8. Okay, so hopefully that all made sense. If not, then please come see me or your professor. I'm always happy to help. My doors are always open. So yeah, I hope you have a good day. And I'm always happy to see you. So thank you. Where is it? Where is it? Okay, bye.